Hello everyone. In this lecture I shall discuss the Euler's method to solve the numerical solution of differential equation. Okay. As you know, you are given a first order differential equation y dash is equal to f of xy, y of x0 is equal to y0. In the previous lecture I have discussed the Taylor series method. Right. In view of the Taylor series method, we have the solution is y of x plus h is yx plus hy dash x plus s square by 2 factorial y double dash x. Right. In general, the Taylor series about xn is yn plus 1 is yxn plus h f xn yn, because your y dash is your f. Okay, y dash is your fxy, y dash is your fxy. So we write it here f xn yn. Similarly, y double dash is nothing but here f dash, is not it, where we find the implicit differentiation. So this is the Taylor series expansion. Now you see, we have to find the derivative of f, right? If this f is complicated to find, or it is difficult to find its higher order derivative, then this Taylor series method is of little use, right? If the derivative is complicated or difficult, then this Taylor series will not work. Okay. Now, if we approximate the Taylor series up to first degree, if we take this first two terms, okay, means this and this first two terms, then we get the Euler's formula. So this Euler's formula is given by yn plus 1 is yxn, yn means yxn plus hf xn yn, and this term becomes here the error term or the remainder term. So this is a second degree term, right? So I write it order of h square. So this Euler method, here this order of h square is my local error. However, we discuss the solution in an interval, right? So in an interval, right, in a given interval, say I is equal to here x0 xn, and xn is equal to say I some point b. Okay, this is my interval. So in an interval, the number of steps is proportional to 1 by h. So thus what will be the total error or global error or the accumulated error? It will be h square into 1 by h square, means order of h, right? So it is order of h square into 1 by h, means order of h. That's why this method is called the first order method. So Euler's method is a first order method. And note that this Euler's method, as we see, agrees with the Taylor series method of degree 1. This Euler's method agrees with the Taylor series of degree 1, as we see, and which is also known as the RK method of order 1. We will discuss in the next lecture. RK means the Runge-Kutta method. Okay. So because of this, we call this is a first order method, or in view of this, we call this is a first order method, right? This is a first order method. So now, before the details of discussion, let me to introduce myself. Myself, Professor Susanta Kumar Paikray, currently working as a professor of mathematics at Veer Surendra University of Technology, Burla, Sambalpur, Odisha, India. Okay. So we see this Euler's method is a first order method. Also I have told you it is a single step method, because in a subsequent step we just use the outcome of the previous step. That's why it is a single step method. So Euler method is a first order single step method. Okay. So leading to the pointwise solution, means in an interval we are moving from x0 to xn with a step length of h. Okay, this h should be small enough, right? Step length of h. That's why we call the pointwise solution of the differential equation. Usually in a case of a differential equation, we get the solution involving the relation between the dependent variable and independent variable, but here we will find the point wise solution, y at x1, y at x2, y at x3, so on, y at xn. Okay, and it is given in a interval this, and here xn is equal to x0 plus nh. This h should be small, h should be small, right? H should be small, and the formula is given by this. Formula is given by yn plus 1 is yn plus hf xn yn. So yn plus 1 means what? Y of xn plus 1, is not it? Y of xn plus 1, and the error agrees with the third term of this Taylor series. So here the error is x square by 2 factorial y double dash at the point zeta. So zeta lies in this interval xn to xn plus h, or alternatively I can write it xn plus theta h, right? Xn plus theta h with 0 less than theta less than 1. However, for error what we will do? Okay, however, for error what we will do? Alternatively, for error we will find true value, true solution minus numerical solution. We just find the error in this way. However, the error formula for the Euler's method is this. Okay, so alternatively, apart from this Taylor series technique, we have an independent approach or geometric approach of this Euler's method. The Euler's method is a simple and basic method in solving the first order differential equation. Subsequently, it can be extended to higher order differential equation and the system of differential equations. Okay, we will discuss in this lecture here. Now, for small increment of h in the given interval x0 to xn, the solution curve, right? The solution curve is almost a straight line, right, or a tangent line. So we have to find the equation of the tangent, and this tangent at which point? At the initial point of the interval. Note that it should be at the initial point of the interval. Okay, so the Euler's method is nothing but the solution of the first order differential equation, and which solution curve is approximated by a tangent at the initial point of the given interval. Okay, so let me to draw the diagram to make you understand. So geometrically we understand it. So we have here x-axis and y-axis. This is x-axis and y-axis. Let the solution curve be this. The solution curve be this. Y is equal to y of x is my solution curve. The real solution of this equation, you say y is equal to yx. Now this solution is approximated by here tangent line. Suppose this is my point x0. I split the x-axis with several nodes. This is x0, this is my x1, this is my x2, so on I continue. x2, so on I continue. Okay, I continue up to my xn. I continue up to my xn, say. I continue up to my xn, right, up to xn. Now this point is my initial point. I have my x0, y0. I draw a tangent at this point. Okay, and this is my x1, y1, right? This is my x1, y1. So this y1 here is my true solution, right? Yn here is my true solution, because from this formula here n is greater than equal to 0. Putting n equal to 0, I find y1. So this y1 is a point here, but the numerical solution is I draw a tangent at this point. So this point intersects this y1 at this point. So now this is my y1, right? y1 approximates numerical solution. my numerical solution. Okay, so this y1, and consequently this gap is the error, is not it? This is your error. So now the solution curve in this interval. So this was the solution curve in this interval, and it is approximated by this tangent line, is not it? So here I can approximate y as your y1 will be, just to find y1, with known y0, with known y0. Okay, here it is the equation of tangent at the point x0 y0. So this is y minus y0 is dy by dx at this point x0 y0 into x minus x0 Now what is my y1? Right, at y1, at here x1 is y of, so what is here y1 here? Y1 means it is y of x1. Okay, so at x1 means here x0 plus h, this is the step length h, this is h. Okay, in this way we will proceed from x0 to xn. So means here x minus x0. So here at x is equal to x1 means x0 plus h. So means what will happen? X minus x0 is here h. Okay, so this is replaced by here h. And what is dy by dx? It is given that dy by dx is f of xy. Okay, at the point x0 y0. So that means here y is equal to, bringing y1 to 0, y0 to this side, y1 plus this dy by dx here is f of x0 y0, and this is your h, Okay, so this is here y this is y0 here, and this is y1. Y minus y0 means y is this at the point x1. So that is here y1 is equal to y0 plus hf x0 y0. You see this agrees with the formula. In your formula, if I substitute n is equal to 0, then what we are getting? y1 is equal to y0 plus hf x0 y0. Similarly, now if we draw the tangent, if we consider next interval, in this interval we'll find in this interval we'll find what? We'll find your y2 will be y1 plus hf x1 y1. Okay, and if you go on continue in the interval xn minus 1 xn, okay, what will get? Here yn will be yn plus 1 will be yn plus hf xn yn. Okay, so this is what the formula of the Euler's formula is derived. Suppose this is my here xn minus 1. Okay, this is my xn minus 1. So now for getting y2 I have to draw a tangent here. Okay, so this is my y2 true solution here. Okay, this is true solution, but this point is my y2 numerical solution, right? Numerical solutions. Now I continue, I go on extending, and I draw a tangent at this point. Okay, I go draw a tangent at this point. So at this point the tangent here, it is my y n plus 1 I am getting here. Okay, y n I am getting here. Okay, and this is the true solution, and this is I am getting it is my numerical solution. Okay, consequently in the interval xn it should be xn plus 1, xn plus 1. Okay, and it is approximated by the tangent at the initial point xn, right? At the initial point xn. So we have, this is the formula for the Euler's method. So consequently the pointwise solution by Euler's method is the sequence of yn, isn't it? We are getting y1 y2 sequence of is the sequence of yn for the sequence of values xn. Here this xn is equally spaced here, means here xn is equal to x0 plus nh with this spacing h, okay, with this spacing h. But you see this process is very slow, right? This process is very slow. The process is very slow. Why very slow? Why it is very slow? Now it is because unless we choose h to be very small, we cannot approach the actual answer. Because why? Because h to be very small, so as to get the result to a desired accuracy. Thus this method is of little use. Okay, this method is very slow. This method is very slow. Why it is very slow? Because unless this h is small enough, okay, we cannot get the desired accuracy. Thus this method is of little practical use. We have to think of improved Euler method. What we will discuss in the subsequent lecture. Now let us solve some example. Now coming to example 1, you are given the differential equation this with this initial condition is this, with the given initial condition is this, and we have to find y of 0.2, means the interval here is 0.02, means we extend 0 to 0.02 with a step length. Let I choose the step length as 0.01. So I need 2 steps here, okay. So h should be very small. You can choose anything to reach from 0 to 0.2. I choose here 0.01. So consequently I have. Also you are asked to approximate the error. Also estimate the error. Now the necessary formula. So this is the necessary formula. Now we have given that x0 is equal to 0, y0 is here 1. Okay, let I choose, let h is equal to my 0.01. So this implies my x1 is equal to 0.01, x2 is equal to 0.02. So I reach at the terminal point here. So now what is your y of x1? Y of x1 or y of 1, this is nothing but y of 0.01. The formula is y0 plus hf x0 y0. So this is equal to y0 is here 1 plus h. What is fxy? Fxy is x square plus y. So this will be x0 square plus y0. Okay, so this is equal to 1 plus 0.01 into 0 square plus 1. So this will be 1.01. Likewise here y of x2 means here y2 means y of here 0.02. It will be y1 plus, putting n is equal to 1, plus h f x1 y1. So this is equal to y1 plus h f x1 y1 means here x1 square plus y1. I substitute all these values. So y1 value here is this, y1 value here, this value is substituted here. That's why this method is a single step method, because the result of the previous step, let it be my step 1, okay, let it be my step 2. So the result of the previous step only is used in the subsequent step. So it is 1.01 plus 0.01 into x1 square. x1 is 0.01 square plus y1 is 1.01. okay, 01. If I simplify it, it will be my 1.020101. So this is my numerical solution here. But what is, if I think of what is the true solution, means we have to solve the differential equation. Okay, we have to solve the differential equation. Here dy by dx is equal to x square plus y of 0 is equal to 1. We solve it. So that means here dy by dx plus minus 1 into y is equal to x square. This is a linear differential equation. So what is the integrating factor? Integrating factor, it is p dy by dx plus pxy is equal to q. So integrating factor is e to the power integral p dx is e to the power minus x. And what is the solution? Y into integrating factor is equal to integral q into integrating factor dx plus some constant. Okay, so this implies I write y into e to the power minus x is integral of x square e to the power minus x dx plus c1. So this is equal to your x square minus e to the power minus x, integration of this minus 2x, and integration of this is e to the power minus x plus derivative of this is 2 minus e to the power minus x plus some c1. Okay, so this is equal to minus of x square plus 2x plus 2 e to the power minus x plus c1. So bringing e to the power minus x to this side, so y is equal to minus of x square plus 2x plus 2 plus c1 e to the power x. Now this is the solutions. We need to find the value of c1 under the given condition y0 is equal to 1. So here y0 is equal to here y0 here y0 is equal to 1, means when x is equal to 0, y equal to 1. If I solve it, here c1 will be 3. So therefore here y is equal to minus of x square plus 2x plus 2 plus 3 e to the power x. So that means what is here y of 0.02? If I substitute the value of x here, we are getting it is 1.020204. It is my true value. So now this gap, okay, this is my true value, this is my numerical value. Okay, if I find this gap, this will be my error. Consequently, the error is true solution minus numerical solution. The true solution is 1.0202204 minus the numerical solution is 1.020101. Okay, whichever is larger, you take larger minus smaller. You may reverse it or you take the modulus. So it will be 0.000103. Okay, so this is the error. Now coming to the second example, dy by dx is equal to x plus y in the interval 0, 1. Or it may be asked to find y of 1. Okay, y of 1 means we have to choose a suitable age here. Okay, coming to the solution, let age is equal to suppose my 0.2. Then what will happen? And estimate the error also, and estimate error. Okay, estimate error. So you see, let h is equal to 0.2. We have x0 is equal to here, x0 is equal to, this is y of 0 is equal to 1. So x0 is equal to here 0 and y0 is equal to here 1. So now, so this implies what is my x1? So that means x1 is 0.2, x2 is 0.4, x3 is 0.6, x4 is 0.8, x5 is 1. So we have to reach at y5, right? We have to continue from this up to y5 I have to find. Okay, y5 I have to find. So what is the necessary formula? necessary formula for Euler's method is yn plus 1 is equal to yn plus hf xn yn with n greater than is equal to 0. Okay, so for n is equal to 1, for n is equal to 0, here y1 is equal to y0 plus hf x0 y0. So this is equal to y0 plus h. The functional value here is x plus y. It is x0 plus y0, x0 plus y0. So you substitute all this value from the previous step, x0 and y0. So this is 1 plus h is 0.2 into 0 plus here 1. Right, this will be 1.2, and it is y1 is nothing but my y of 0.2 is my this. Consequently, for n is equal to 1, for n is equal to 1, I am getting y2 is y of 0.4. It is y1 plus hf x1 y1. Okay, so this is your y1 plus h. The functional value here is x1 plus y1. So I just substitute the value from the previous step. This is 1.2 and x1 is here 0.2. So if I substitute it is 1.2 plus 0.2 into here 0.2 plus y1 is 1.2. It is my 1.48. Likewise my y of 0.6 will be 1.856. Then y of, if I continue here, okay, y of 0.8 will be my 2.3472, and y of 1.0 is my 2.97664. If I think of the true solution, likewise my true solution will be y is equal to minus of 1 plus x plus 2e to the power x, and y at 1.0 is my substitute of the value of x is 1.0, it is 3.436. So it is my true solution and it is my numerical solution, and this gap is my error. So what is my error here? The error here is 3.436 minus 2.97664. So you see this error is 3.436. You see this error is very high. Sorry, it is 0.